when the metro rail came to Dhaka, it was like a dream country for all the citizens of this city. People had been struggling for 4 or 5 years because of the construction of this metro rail system, and now it's almost complete. And all of the platforms of these metro rails are fully digitalized. Uh, if you think about from controlling the arrival to departure of the metros, and from tickets to crowd management, everything is digitalized. Even if you think about these 100 years ago, it would be a laughable thing. That how can you control these things digitally? See, this is simply extraordinary. That these inventions of semiconductors and digital electronics has brought us. So hello everyone, I'm Mohammad Moinul Islam, and I'll be presenting my OBE assignment in this video on an automatic crowd management system at the platform entry of metro stations. I was given some instructions and some requirements and a scenario for this assignment. I won't go into those details, as I believe whoever is watching this video is already familiar with them. So I'll deep dive into the block diagram I have created for this system. I'll also go through my assignment pages so that you can relate. And sorry for the exposure of the text. It's written on pencil, so I'm sorry. At first we have 4 RFID sensors. Apparently the passengers of our metro systems carries an NFC card or an RFID card, RFID sensor cards. So those cards have RFID sensors, so we can detect these RFID cards into our entrance. So I have placed 4 RFID machines there, if you say, that detects the RFID sensors or RFID cards. So if they detects, they sends an analog pulse or analog signal, I must say, and I converted those analog signal into a digital signal with an ADC, analog to digital converter. This is a 1-bit ADC, so every entrance is connected with an 1-bit ADC, and I have named them with D1, D2, D3 and D4, and they are actually giving me outputs as high or low digital signal. So I have sent those digital signal into this pulse synchronizer. Now what's this pulse synchronizer, I will explain it later. And I also send them into the alarm logic, all of these signals into alarm logic. And apparently we have a requirement that if more than 3 passengers cross the yellow line, that means the entrance of metro station, there will be an alarm that should trigger. So it goes into this alarm logic, and the logic will be explained later. And according to that logic, an alarm unit gets activated, and that alarm unit is powered by a 5510 clock. So that goes one of our requirement, that if 3 passengers cross the yellow line simultaneously, an alarm goes on. Then comes this pulse synchronizer. Actually we have as this is a crowd management system, we need to count the crowds. So if we want to count the crowds, we need to have some counters. This is a 4-bit counter which counts the passengers on the platform, and this is an up and down counter. So if some passengers exits through this RFID, this is also connected with a 1-bit ADC. If someone exits through this RFID, so this counter goes downwards, and if it gets an hit from these entrances, it goes upward. So this is an up and down synchronous counter, and this is a mod 10 counter because one of our requirement is only 10 passengers are allowed on the platform at a time. So if there is more than 10% trying to enter into the, if there is already 10% in the station, and if someone else tries to enter, it will stop it. And how will it stop it? With an FSM. I will explain I'll go through the FSM, and before that I will explain this counter. This is a typo here, so it should be 5-bit counter. I have added there 5-bit counter. So it's a 5-bit counter, and this counts the tickets which are being registered. So tickets, apparently if you have a ticket, you will go through the entrance. If you go through the entrance, this will count. And this is not an up down 4-bit counter, this is a typo, as I copied it from this one. So This is a typo. This is basically an up counter. I have added it here. So synchronous up counter, and this is a 5-bit up counter and mod 20. So this counter actually uh, track each of the entrance and count it upward. It doesn't connect it. It is not connected with this exit RFID, because if someone exits, then exits, no problem. He already bought a ticket. That's why he went into the station. So this is actually our ticket counter. So according to our requirement, if only 10 passengers are allowed on the platform, and 20 tickets, if I'm not wrong, 20 tickets are issued in a day at maximum. So that's why I've added a 10 mod counter, up and down counter, which can track entrance and exit, and an up counter which can track the entrance. And both of them are simultaneous. Both of them are mod 10 and mod 20 counter. One of them is mod 10 and one of them is mod 20 counter. So the output of these counters goes into this block. This is called next state block. Basically, here comes our FSM. Okay, here comes our FSM. These are state machine, finite state machine, and the next state logic is counted based on the present state of the register and the outputs of these counters. So we'll explain the FSM later broadly. This is our FSM module, and lastly we have a control room where a 4-bit DAC is placed. So basically, according to our requirements, in the control room, they need to see the passenger count at the platform. So this counter is connected with this 4-bit DAC, and they can apparently see only the analog signal. So I've added a DAC, 4-bit DAC. So as this is a 4-bit counter, so it sends a 4-bit signal, and this 4-bit signal comes into this DAC, digital to analog converter, and it converts into an analog signal which can be read by the control zone. So there goes our block diagram. I have given the block diagram for you here. I did not add the bit numbers on those areas. I have added them here. This is a 5-bit counter, so it returns a 5-bit output, and this is a 4-bit counter, so it returns a 4-bit output. And our state management is a 3-bit. There is a typo here again. 3-bit, that should be 3-bit. Our state management system is a 3-bit counter. 3-bit register, so it returns a 3-bit output, so that should be 3. This is a typo, I'm sorry again for the typing mistake, for writing mistake, whatever you say. And I have given a overall reset button here. So I did not add the connections to all the registers here because it would make the whole diagram messy. So basically, when you press this overall reset button, all of the registers and the whole system goes in reset. So everything starts from suppose I am starting a new day, so you press the overall reset button and the whole system goes reset. So this is our block diagram. We have explained the alarm logic here, right? So let's go through the alarm logic. So remember, I have D1, D2, D3 and D4 outputs of entrance. So there are 4 entrance. So if 3 passengers cross the yellow line simultaneously, it should trigger the alarm. So if we calculate the combinations of 3, it should be 4 combinations 3, 4, 6, which is actually 4. So you can find at most 4 combinations of entrances. So these are all 4 combinations. So if D1, D2, D3 goes high at a time, or D2, D3, D4 goes high at a time, or D3, D4, D1 and D4, D1, D2 goes high at a time. Sorry, or if any of these combinations goes high at a time, it should give an high output to this Y signal. I tried to minimize this equation with KMF, but this is our simplest equation, so we couldn't find any other simpler equation than this. And this equation is developed with NAND gates only, according to our requirement. Only NAND gates. So this is the NAND gates implementation. And see, there is a manual disable switch, and this is an active low switch. So if you press 0, basically that's the active mode of this button. So if you press this button, the alarm is already triggered, right? We need to turn off the alarm, right? So that's why I place the manual disable switch here. So if you press this button, the whole alarm should turn off. So it is what it is. And remember, this is an active law button, so that's why I connected with AND gate. Okay. Sorry, NAND gate. So basically AND gate, I connected with NAND. I designed it with NAND gate. So that goes our alarm logic unit. If this alarm logic is on, then we'll need a 555 timer IC to generate an alarm. So for that we have some requirements that according to my ID I need to compute the frequency of this 555 timer IC, and the duty cycle also that needed to be counted and computed from my ID. My ID is 53338. So if you add them together, you get 22, and that's our Q value. That's a P value. That's our P value, and apparently we need Q hertz. Q percent duty cycle. So Q is computed from 100 minus P, so that becomes 78. So I need a 78% duty cycle, and I need a P5. P is apparently this 5 plus 3 plus 3 plus 3 plus 8, which is 22. So if I add 225, that is less than 250 hertz. So as a requirement, I need to replace it with an 400 hertz frequency. So my frequency is computed 400 hertz, and duty cycle 78%. So we calculated from the frequency equation, from the frequency equation, and calculated the R1 and R2. We have derived two equations basically from frequency and the duty cycle equation. Two equations are here. This is our first equation. These are second equation. So from these two equations, we actually got the resistor value. So again, we need a capacitor for timer IC. So we have given three different capacitor choices. 50 microfarad, 250 microfarad, and 470 microfarad. So I have computed all the resistors for 50 microfarad and 250 microfarad and 470 microfarad. And the lowest resistors we got is for 470 microfarad, and the highest resistors we got is for 50 microfarad, which is 51.61 ohm and 20.24 ohm. Now we choose the 50 microfarad and these two resistors. Why? I have explained it here. So basically our 555 timer IC is not that how would I say, it's very vulnerable. Is very vulnerable in what sense? If we pass higher currents, there might have heating issues, and that could damage our IC, and also our circuits. Also we can damage our circuit, because if we pass higher current, it will give us it will consume high powers. So if we consume more power, then our circuit will get heated more, and it can be damaged. And also a large capacitor can have leakage current, and that can cause inaccurate timing. That's why smaller capacitors are generally better for a 555 timer, because it is actually a timer IC. We need to efficiently count times. So we used 50 microfarad as a better choice, and for that we have used we got these two resistors, 51.61 and 20.24 ohm resistors, and those are the highest resistors we got for these combinations. So we need to use them. Practically, all of these combinations are not practically usable, because these are very small capacitors. So we will have issues on that. So with that capacitor and resistors, we have designed this 555 timer circuit. See the Y1 signal. We have got this Y1 signal from this manual disable switch. So if you want to disable it, we can use this with this manual switch. So that's why I have added this with an AND gate. So if you get only one signal, that the alarm should trigger, it will actually turn on the alarm circuit. If it goes off, then this will turn off the alarm circuit. So this is our 555 timer IC. Next let's go to the FSM, finite state machinery. So for that we have simplified some things, suppose such as heat. So apparently how can we detect an entrance, that someone is entering? We can detect it by an heat. How an heat is calculated? If any of these ADC sensors, if any of these ADC blocks gets high pulse, that means someone is trying to enter, right? So if we OR these signals, we can get a hit. We can rely on that hit, that if hit goes high, that means someone is trying to enter. Okay, someone is trying to enter, fine. Then we need the count output from the mod counter. So see that we have logic that more than 10 people cannot enter into the platforms at a time. I mean, more than 10 people cannot stay at the platform at a time. So if the platform passenger count is 10, we cannot enter, we cannot let anyone into the metro station. And also only 20 tickets are issued. So if the ticket count is already 20, if someone is trying to enter again, that means someone is trying to do fraudulent activities or something like that, because only 20 tickets are issued by the authority. So if 21 ticket is coming, there must have some issues. It will not allow the passengers to enter. So that's why we need a let's assume that the count output we get from the mod counter 10 mod 10 counter be C0, C1, C2 and C3, and the output from the mod counter 20 be B0, B1, B2, B3 and B4. So these are our outputs. So if that's 10, how can we sense that? See, remember, if someone is trying to enter, that means we already counted 10, right? So if it counted 10, the system gets as it's a mod 10 counter, it will be resetted, but the system initially gets the hit that 11 is hit, 11 signal is hit. So and also goes for this one, that 21st signal is already hit, as it's already counted. So and of course if it's counted 10 and 20, it will go reset, the counters will go reset. So I have tackled that with different things here, so I will explain it later. So the binary for 10 is 1010. So I have given the expression for 1010, and the 10100 is for mod 20 for 20. So this is the signal for BM20. That means if this goes high, that means we got 11 signal. If this BM20 goes high, that means we got our 21 signal in the ticket counter. So let's then comes our checking signal. So checking signal must be the end output of these two signals. That means any of them, if any of them is false, that means my check is actually false. So we cannot let the user go, right? So if this check is complete, we can say that everyone is going through the process. Everyone is actually the ticket counter is not exceeded 20, and the mod counter is not and the passenger count is not more than 20, so we can let the passenger in. So this C is actually our checking logic for the FSM. Now comes our FSM transitions. This is a state chart diagram. So initially I'm at idle state. So idle state is counted with 000, and this is a binary counter 000, 001 and so on. So initially I'm at idle state. If I get a hit, that means if I get any hit from these sensors, I will go to the checking state. Okay. So if I get a hit, I will go to the check state. If I in the check state, I will check if the check is 0 or not. If that's 0, that means we have an unwanted entrance, so we cannot let the gate open, so it will go to idle state again. But if I get an high, that means the check is completed and check is valid, then the gate is turned on, the gate is open. It will stay open for 3 clock. I have used a 1 Hz clock, that means 3 seconds, so it will stay for open for 1 clock, 2 clock, 3 clock, and then it will close. After the 3rd clock it will close the gate. So after the if the gate is closed, then it will go back to the idle mode. The next clock, on the next clock it will go to the idle mode, and that's how the cycle continues. And these are reset button, so if I press reset, then wherever I am, it will be in the idle state. So this is our transition table, so you can look into the transition table. So according and we don't have any output here in this from this FSM. Basically these are states, so according to these states we need to perform action, such as if we actually reset the whole state machine, then it will reset the whole FSM, and on the 0 state it stays idle. In the idle state it stays there. On 001 it checks the conditions, and 010 it open the gate, and on the 010 it resets the mod. There comes the thing. See, I've told you that mod counter goes to 0 again. So if someone tries to enter into the entrance again, it will count it as 1, right? So that's an issue, right? So we need to reset the mod counter back to 9 actually. So the reset we in this state, in this 010 set, where the check is failed, it is going to idle again. So if the check is failed, then we need to perform an action based on this state. So it will reset the counters back to the binary 9 or and binary 20, binary 19 actually. By 19 and binary 10 it will reset the counters into back to the peak limit, seal limit, and for that we need an extra module, and this is also a limitation for this whole circuit, that we did not add any module for the reset of that counter. So this is a limitation. So I'll explain these limitations later into the presentation. So next comes the delay. So for 3 seconds it delays, and then goes to the idle mode again. So according to this transition table, we have made made these equations. So with these equations we can actually build our finite state machine. So that goes our finite state machine, and that is our Verilog code for finite state machine. So this is our code, Verilog code for finite state machine, Verilog code for finite state machine. And at 5th point, we have been asked to show how the DAC output voltage represents the passenger count for 5 and 10 passengers. They let us assume that 4-bit, we need to use a 4-bit DAC and V reference 5 volts. So if you use a 4-bit DAC, the V out equation goes like that, and we get a 3.125 volt for the passenger count 5, and for the passenger count 10 we get 6.25 voltage output into this digital to analog converter, and the V reference is definitely 5 volt. Next, so this is our whole system more or less, but we have a lot of limitations in this circuit. Let's go through one by one. Firstly, this is a prototype system, so it has a lot of limitations, and we must ignore them for these cases, because this is a very simplified system. This is not a complex system. So the first limitation that I have noticed is the sensor inputs. The ADC inputs. See, these ADC inputs, they are coming to the pulse synchronizer. Now this pulse synchronizer is not probably explained in this system because of lack of knowledge, you might say. I don't have enough knowledge, or this TLC syllabus did not cover how can we actually synchronize these signals and send it as a clock, because the counters needs clock, right? So if you can't pass the signals directly into the counter, it won't work. So we need to send signals, send a clock signal. So we need to make a clock signal with this pulse. So I assume that if we use a piezo resistor and some capacitor or something like that, if we do some things, and we can make a pulse synchronizer that can work as a clock. So I cannot implement. I did not implement it, and I couldn't. So that's a limitation. And there can have frequency related issues because this state machine is a 1 Hz state machine, and the counters here are very high pulse counters because we need to detect the entrances, right? So there might have frequency related issues if we implement it practically, or go through more theory. We might got some frequency related errors or frequency mismatches, so that can cause issues in the circuit. uh, and I have said it earlier that if on the FSM state machines, if we get more than 10 counts, it will reset to 000 as a counter property, but we cannot reset it to 000 because we need to we also need to stop the next passenger who is coming, right? So that's why we need to reset the counters into the into the previous state, the 9 and 21 state, 19th state. So we need to reset it, so we need a extra module for that, but I did not implement it here as this is also not a requirement for the project, for the assessment, so I did not implement it. These are limitations. And the up down counter, this can have some issues because the exit is directly connected to this synchronizer. So how can we, so there can have a logical error here, so we cannot send it directly to the counter as a down signal or something like that. We need to have some logical boundaries here, and I did not cover it, so this is a limitation. And of course this exit RFID, this is also not broadly explained here. This is a new component that I introduced in this assessment, so this can be added as a limitation. So these are my limitations in this whole system, and that goes my whole presentation of this OPE assessment. And thank you so much for watching this presentation. We understood the whole scenario, and that's it. Thank you so much.